Covering over some load cell basics today. We're going to go through the scenario as though you have a sensor, and you may not know exactly what it is or exactly how to use it. So we're going to go through the information to be able to confirm what you have, get the necessary info on some of the details maybe about that particular unit, and also know how to install it. All right, so as I said, these are kind of the talking points today. We're also going to be covering, again, the installation and best practices to use it. And we're going to cover a couple different models of popular interface load cells. So, all right, well, the first step should be pretty straightforward, and that's going to be a physical inspection. You want to make sure the sensor looks like it's in good working condition. Some visual clues would be the thread details, any signs of rust if it's been left out in the elements for too long, where it shouldn't have been. Or if it's just physically damaged in any way, it could include the connector as well. So make sure the pins all look healthy in that regard as well. If you've got a new unit, then that's pretty straightforward, and we can move on to the next step there. All right. So reading the label. Our labels do a pretty good job of giving you some basic information on the units. They vary somewhat by different models. The low profile there at the top, that's the round blue one. That's going to have a model number like you see in the label there. It's going to have model, capacity, serial number, and also the rated output from the actual calibration data. We're going to get a little more detail in terms of how to understand the 1200 series. But basically that's the format you're looking at. You're going to have the capacity, the series, which would be a 1200 series, the model size, which correlates to the capacity. In this sense, it's a 1210. There'll be some letters on there which are going to refer to a specific option code. We have a few common codes for those, but if you have a series of letters that don't make sense or you can't find anything on the website, please call the factory. Capacity should be straightforward. That would be either in pounds force or potentially newtons. And then again, the output's going to tell you what kind of load cell it is, if it's in millivolt per volt or if it's amplified. Moving down to the SM, again, similar. You have the model designation first, then the capacity, and then after that typically is where we have our option codes. In this case, it's a -19. The 19 happens to refer to the cable length. But again, if you see extra numbers on your model, you probably want to call in and have us tell you what you've got there if you don't already know. But again, capacity information, which will tell you the expected output, full scale, and also serial. And then for the WMC, that follows a similar format to the SM, where you're going to have the option code at the end of the model number. And again, in this case, this would have a special length cable on it with the same -19. All right, so now that you've found the model number, and you may need to find some more information, well, obviously we've got datasheets available for our products online. Datasheets are a good place to go to just confirm, again, what you have. We're going to talk on a couple things here, but I want to show you our newer format we're rolling out here. It does include wiring diagrams and basic option code information down in the bottom right, and we're going to be implementing this on all of our products moving forward, so that should be very useful. As you can see down there in the bottom right, maybe tough to read on your screen, but we've got connector details, AJ, AF, ACK. Those, for those of you familiar with our load cells, know that would correlate to a screw type, bayonet type, or integral cable on those. Not in that order. All right. Looking in at the closer look at the data sheet here, we've got our model information across the top. I just wanted to highlight that we often have different capacities all under the same form factor. So, for example, the 1210 model is available in, let's say, 300, 500, 1K, 2K, 5K, and 10K capacities, all with the same form factor dimensions below that. Oftentimes customers don't realize that, so I just wanted to touch on that. And again, each one of those is going to have a full-scale output corresponding to the load cell for that capacity. And you can see as we jump over the 1220, now we've got different capacities for that form factor. And then as we move over to the 1232, that's going to be for our 100K size. So, also on the data sheet, you'll be able to see performance data as well as expected output, such as our 2.0 nominal, 2.0 or 4.0 on the majority of our capacities, millivolt per volt nominal output on there. Max excitation, that's also a good one to pick up on the data sheet. and also kind of what to expect as far as the zero balance goes. We're going to talk a little bit later about why that may be important to note. Other parameters such as safe overload, standard product is usually for 150% of capacity. That's something you need to make sure is appropriate for your application as well. And then there's connector information for the standard model, and also what cal data to expect. TNC is going to mean you're going to get both tension and compression cal data for that unit. Speaking of calibration, here's an example of a cal cert for a low profile. This is a 1210 model here, just like we talked about. ACK is going to refer to the bayonet connector, 10K, and then the dash B means it has a base on it. We're going to show you some pictures and talk a little bit about bases as well later on. But the load cell cal cert is going to have some good information with regards to how the unit was calibrated, how it performed, and also some information you can use for potential troubleshooting down the road if you need to, or for just, I would say, system health checks. So zooming in a little bit, again, we reference the model number, serial number. Bridge A is referenced there. If you have a multi-bridge sensor, meaning you have two connectors or two outputs, you'd have a separate sheet for the bridge B also. Below that, we've got some basic health information as recorded during calibration, test conditions, including the excitation voltage that's used during the calibration. Then below that, traceability information. So that's these items are basically what we were using here to calibrate the sensor, and we have full traceability in that regard there. Below that, we've got shunt calibration, and then performance summary, and the actual data for the calibration. Now, on the performance summary, we have both our rated output as well as SED output, nonlinearity, hysteresis, and the SEB. So these are the parameters that we're holding the units to make sure they meet spec per the datasheet. And again, the datasheet values you saw earlier were nominal value, or worst case values when it comes to performance. Typically, you're going to find an interface load cell performing at 2 times that spec. But important to note here again, SEB, you may see that and hear that. We've got more information online, but to take away, it's essentially the best fit straight line, taking the nonlinearity hysteresis into account for that unit. Backing up to the shunt cal data, this is useful to be able to check the load cell health at a future date. So we use a resistor on there. We shunt specific legs to simulate an output for either the tension or compression mode, and we record what that actual output is. This is something that you can usually utilize in your instrumentation later on down the road to just do a sanity check and make sure the load cell is still giving about the same output, which would be a good indicator of the health of the bridge. So again, CalCert's a great source for excitation, expected performance, as well as output. Again, you'll see a millivolt per volt output here, whereas if it's an amplified unit, you're probably going to see whatever the high-level output is on there. Fundamentals, I'm going to pass this over to Elliot here.
All right.
Go over some load cell basics.
All right, so the load cell fundamentals, essentially you're going to use the load cell in one of 2 ways, either in a bipolar, like for universal application, or be using it both in tension and compression, or in a single mode, either only tension or only compression, and that's going to dictate what output you get from the load cell. Most of our load cells are going to be a tension upscale device, meaning you're going to get a positive output when a load cell is placed in tension. And so also correlate with your calibration certificate as previously referenced. Standard output from the vast majority of our load cells is going to be an unamplified millivolt to volt ratiometric signal. We'll come back and hit that again a little bit here. We do have amplified signals available as well. Oftentimes customers will require that to interface their data acquisition units. Some examples of amplified unipolar signals would be a 0 to 5 volt output, or a 0 to 10 volt, or a 4 to 20 signal. Examples of bipolar amplified outputs would be plus or minus 5 volts, plus or minus 10 volts, and in some instances 12 plus or minus 8 milliamps. Again, the unamplified output is going to be a ratiometric millivolt to volt output, and we got some examples on the next slide here. All right, so in this example, we've got a 5,000-pound load cell. connected to an instrument of some kind. In this case, this is our 9840. And then we have a load placed on the load cell. So again, we're going to assume a nominal output of 4 millivolts per volt, and assuming 10 volts of excitation, that means at full scale with 5,000 pounds on the load cell, you would see a nominal output of 40 millivolts at 5,000 pounds. A variation of this would be if we only supplied 5 volts of excitation, we would expect half of the output, or 20 millivolts at 5,000 pounds. Naturally, you're going to want to have some way of interpreting the output or the voltage from the load cell. So you're going to be connecting it to instrumentation of some kind in the application. As far as connectivity goes, if you're looking to hook up the load cell and need information on that, we have the majority of our wiring diagrams are available online. If you're not sure about what wiring output or what wiring configuration you do have, please do give us a call. We don't mind. We would have that information available for you for any unique option codes you may have. Signal leads, we have 4-wire and 6-wire configurations on these load cells. 6-wire is going to offer something called sense. Some instrumentation may support that. If you order a cable from Interface for like a standard low profile load cell, our standard 6-wire cable will support that sense function. For other applications, most times you can get away with just pairing that with excitation. Obviously, we would recommend using the proper cabling, shielded conductors, and avoiding ground loops in any wiring. Excitation voltage, as Brian discussed earlier, on the calibration certificate and the test conditions portion, it's going to reference the voltage of excitation that the load cell was calibrated at, and typically that would be a recommendation for usage. So if a load cell was calibrated at 10 volts, we would recommend operating it at 10 volts. Some of our smaller load cells, such as perhaps an LBM or an LBS load cell, due to the small size, may require a little bit less excitation. They may have a nominal excitation of 5 volts instead of 10. This would be to eliminate any potential for heating in the gauges. Once you start hooking up the instrumentation, you're going to be looking for how to actually scale it. And there's a lot of options there for how you would scale instrumentation. Some instrumentation options will take a millivolt to volt entry. Others will require a known load or a shunt cal of some kind. The bottom line is you're going to be referencing that calibration certificate in some way to get scaling data off there. Lots of options there. Now, once you get hooked up to the instrumentation, you can do some further diagnostics on the load cell, particularly if it's an older unit. There's a couple things you can check to establish the health of the load cell. Number one would be zero balance. If the load cell has been in use for a while, it'd be good to do a sanity check on the load cell. The zero balance is going to be a good check to see if there's been any potential overload or damage to the load cell. If that zero balance is shifted, let's say you have an increased zero balance, let's say it's a negative, it's shifted up or down some way from the nominal, that's an indication of potential damage. Doing a verification of the R-cal or shunt cal is also another good thing you can do. Again, if you see any shift from there, or significant shift I should say, it may be a good idea to get that evaluated. And then if you are suspecting issues with the load cell, please contact us. We do have some more tools you can use to evaluate the bridge of the load cell using a multimeter or other instrumentation options. So we're going to kick it over back to Brian, and we're going to talk about three of our most common or three of our popular load cell options: our 1200 low profile series, the SM series, and the WMC series.
All right. As Elliot said, we're going to be covering three of our more popular options, or products, I would say, our LPs, SMs, and WMCs. We're going to go over just a few talking points to get the best performance possible out of these. Obviously, the load cells are going to give you a signal regardless of how they're loaded, but to get the most accurate data, there's some tricks you usually want to follow. So the first one we're going to be talking about is our low profile. That should be a familiar load cell to interface customers, or interface users, I should say. It's known for its very high performance, high output, and its insensitivity to off-axis loads. Also, temperature performance typically can't be beat on these units. Here's a particular unit shown without a base. Again, we're going to talk about that in a minute here in terms of what the benefits may be from that. So mechanical installation, you've got your load cell, you've got it hooked up, you've got your instrument scaled, now you want to get it installed and start using it. Well, there's some things you want to follow from a mechanical attachment standpoint. You can see here is the production unit on one of our cal frames, not quite painted up yet. We've got it threaded in there. You want to make sure when you're threading into what we call the live end of the load cell, which is the center hub on the LP, that you've got enough threads engaging into the load cell itself. If you're getting a load cell with a base, it's going to have a plug inside there, so we usually recommend threading in to where the stud bottoms out and then backing it off half to a turn just to make sure that it's not pushing on that plug. But at that point, you're going to ensure that you've got good thread engagement. The next step that we do for calibration, and again to get the best performance, is we would attempt to preload the load cell. So we would actually put a tension load on it to about 130% of capacity and lightly jam the jam nut. And what we're doing there is we're ensuring that we won't have any repeatability issues due to thread engagement changing through the center of that flexure. So if you can't provide a preload on the load cell, then we do have some torque values available in our installation guide that will do a pretty good job of getting the threads loaded up in a similar fashion. But again, the whole point with the preload is that we've got the threads engaged to a point that is higher than the load cell should see during use. And by doing that, it's just going to help with repeatability and for best performance. Now, the load cell you see there is actually bolted up to a base. If you can see my cursor here, we've got another picture shown specifically, but that's the lower half of the load cell. Always recommend using high-quality hardware, grade 8 or better, when you install it either to a base or to your own mounting plate. We recommend that whatever you mount it to is 2 10,000ths total flatness, and our bases are typically RC30 to 33 on the hardness scale. When you are installing it, we recommend following a star pattern just like you would torque a wheel on a car. Now here's some examples of our LPs. The left one is installed on a base, which is then installed to a mounting structure or some sort of it may be a hydraulic actuator. And then on the top side, we've got a rod end bearing and a clevis. We typically recommend introducing some rod ends if possible or clevises just to minimize the amount of bending moment that may be exerted on the load cells. As you know, these are typically axial sensors, and while the low profile does a good job of rejecting bending and off-axis loading, it's always good practice to try to reduce the possibility from that in the first place. So again, here's a load cell pre-installed on a base on the left, and here's an example of a low profile on the plate itself, or a customer's plate or a fixture. And as we mentioned, really want to have a nice hard flat surface for that load cell to react against. Parallel as well is very helpful. In this case, you see a calibration adapter pre-installed on the load cell. That is a feature we offer. In fact, if you look at our calibration grade sensors on our website, you're going to see that they all come with these. Well, why do they come with them? Well, like I mentioned earlier, we recommend preloading. And it's often easier for customers to go with a calibration adapter where we'll preload it here at the factory and calibrate it that way so that you'll be able to attach on the calibration adapter end and have good results moving forward that way. So talking about bases, bases are a very convenient way to basically get the same performance out of your application that we get on the cal frames. Again, we calibrate on bases. If you get a base with your load cell, you won't have to worry about all those plate details and making sure things are flat and hard, and it's a lot easier to integrate into your assembly. You end up with a female threaded hole on the top and a female threaded hole on the bottom. Works really well for, again, using them inline on hydraulic actuators and such like that. So typically we recommend customers go with bases if possible. Just makes things typically easier in the end run. All right, so the last part is just a double check and making sure that the load cell is well suited for your application. You want to think about things such as, well, do I need a fatigue sensor for this? What about overload conditions? What about environmental conditions? Do I need to worry about moisture or things like that? And Interface has solutions for all these. And again, if you're not sure, call the factory, because oftentimes your idea of fatigue, a couple 100,000 cycles is really a non-issue for our low profiles, which are good for a couple million fully reverse before you even move to the fatigue. So again, these are just things to think about. Minimize those off-axis loads if possible. Applies for LPs and other sensors. That's going to give you the best performance there.
All right, so another variation of our 1200 series low profile series would be the low profile compression only version of these load cells. You'll notice they have an integrated spherical load button. It's a very convenient loading surface. Also it gets a little smaller dimensionally. You'll notice we have counterboard base mounting holes on this particular load cell that's pictured. That also helps to minimize any induced bending moments. That spherical load button should be the only curved surface in the load string. And again, like with the standard universal 1200 series, we would recommend a hard, flat loading surface, flat within 2/10,000ths. We would assume a RC to 30 to 33 hardness on that surface. And then any bearing plates that are going to interface with that spherical load button, we would recommend be hardened to RC 45. And we have a couple examples of what this would look like. Again, we have a compression-only cell with the base installed. We have a bearing plate with a flat surface. I'm going to single point of contact on that. And again, hardened to the specification. And then the compression-only load cell with no base installed on a mounting plate. Again, with those same scenarios. All right, moving on to another one of our popular load cells here in Interface is our SM series. This is a smaller size load cell than a low profile. It's 3 millivolt nominal output. It is it's an economical choice if you're dealing with a budget of some kind. Very, very handy for tension use. Uses our proprietary interface strain gauges, and is still suitable for tension and compression use. Environmentally, you want to make sure it's also suitable for the environment, as previously discussed. We do have a sealed version of this available. It's called the model SSM for applications with environmental concerns. Okay, so installing this load cell, much like Brian discussed a little bit earlier, we want to have this installed in the load string such that we're minimizing the potential for any bending moment. This load cell is a little more susceptible to bending moment than the low profile series due to the lack of moment compensation. But again, very highly performing, provided we're minimizing those bending moments. We would recommend in installation jamming lightly on the flexure, and then obviously some rod end bearings or something to minimize those bending moments. This load cell, it's important to make sure that the live end and dead end are oriented correctly. We'll have an illustration coming up here next that'll illustrate that a little more. And then strain relieving the cable and securing it in some way, so we're not cycling that cable through and potentially fatiguing it. All right, so this is a good depiction of live end versus dead end. I'm sorry. You'll notice that the cable and the mount surface are separate from the live end of the load cell. So we would want to make sure that the load, or what you're trying to measure, is applied to the live end, and that you'll be mounting to the dead end of that load cell. We don't want the cable or the mounting surface to somehow impact the measurement you're trying to take. In installation here, if you're working on jamming the flexure, you can see the depiction here. You're wanting to make sure that you're not transmitting any torque through the gauged area and potentially damaging the gauges through any moment being applied.
All right, moving on now to our WMC series. These are very popular stainless steel load cells used for tension and compression. They're very popular due to their small size and the fact that they're stainless steel and are sealed. These are often an easy go-to for doing basic testing. They have similar installation notes to the SM. Again, we'd recommend using rod ends if possible. Unlike the SM where you're kind of loading through the flexure itself, these you're going to be loading through the studs. So while it may not be easy to see on that picture, we recommend you don't bottom out the attachment hardware. You don't really need to jam them either. You can. We do have torque values available on that, but they typically perform best if you leave those just a little bit loose, since again you're loading through the studs on these sensors. As you mentioned, pay attention to the cable. These have pretty good strain relief on them from the factory, but that cable can still often influence your measurement if you're not paying attention to how it's secured, especially in the dynamic tests where you may have some inertial influences on the measurement you're taking. Pretty straightforward though. So we're about wrapping this up. Hopefully we did a good job of explaining how to inspect your load cell, how to understand the model code, to help figure out where you can find more information, especially with regards to what kind of signal to expect from it, and then also what to do with that signal. We've got a lot we could talk about instrumentation, but hopefully, again, you've got the basics there, and then with the mechanical installation, you have a good handle on how to put it into your assembly and how to impart the load through the sensor to get the best results possible. So